So, today in the 30th lecture in module 2 we will talk about the fluid structure interaction part 2, where we discussed yesterday something on wave structure interaction. So, we must understand and appreciate that we are looking at a system of this order, where for a given offshore structure the inertia force are very high because the top side mass of the given system is very high, significantly large, and the system can either be flexible or stiff enough to recenter, to enable the recentering capability. We are looking at the right hand side of the equation of motion f of t, where when we say that in a given flow field, if member interferes with the flow domain in the vicinity of the member, the vicinity of this member, what would be the consequences occurring because of the fluid interacting with the structure. More interestingly, this has been a very challenging problem in offshore structural design itself right from the beginning, and to avoid and alleviate these kind of forces effectively, people started anchoring this cylinder to the sea floor as a permanent system, so that they have a fixed set base, so that the response given by the system back to the environment or vicinity around the flow field is minimal. So, there are two kinds of forces coming in. One is the vibration induced on the member because of the continuous flow of the water particles, which is called as a flow field domain. The second is the secondary vibration or oscillation generated by the system itself, even if it is fixed. Of course, in the case of floating, no question, it will anyway happen. Even if it is fixed, it will have a secondary vibration around the vicinity of this in both the direction, inline flow and the transverse flow both, which we saw in the last lecture. We will continue to do that now. We will see some of the important points, then we will talk about the summary. We look at the wave structure interaction. We already said that when waves pass a cylinder, it causes oscillation in line force on the cylinder. In addition, free surface also changes in case of a submerged cylinder. Large structures, on the other hand, if the diameter of the structure with respect to the wavelength is comparatively or significantly very large, when they are placed in the wave field, they alter the incident waves in its vicinity. Please understand, they do not alter the wave on the downstream side. This is an upstream side, there is an upstream side, there is a downstream side. There is a pressure difference between these two, which relates in a differential shear, which we already saw in the last lecture. So, near the vicinity in the upstream side, the wave approach side, it has got lot of disturbances created when the cylinder or the member interferes with the flow field. However, this interference will settle after the wave passed the cylinder and a specific length, which we call as characteristic length of the given problem. So, this is actually the boundary element of the given analysis, which we will talk about this later in the coming lectures in this module. So, beyond which the interference effect on the cylinder on the wave field or the flow field will be not significant at all. So, if you want really mathematically or numerically model the behavior of fluid structure interaction, your domain should encounter or capable of encountering the whole disturbances in the inline as well as transverse direction, numerically as well as experimentally. Okay. So, that is what the idea is. We all understand that how it is generally done, but still, however, we must emphasize that when large structures are placed in the wave field, the wave field incident waves in the wave field in the near vicinity gets altered significantly, and of course, if the dimension of the structure is too large compared to the wavelength, then the flow remains attached to the cylinder, and that becomes a problem, because if the cylinder is also an oscillating body, then it creates vibration automatically because the flow is attached to the cylinder. When the flow separates, then you can see the effect of the separation of the flow field will have a nullifying effect on the vibration of the system. When it gets attached to the structure, so it adopts the vibration of the structure itself, which is very bad. Now, to explain this philosophy, there are several procedures available in the literature. One can use the potential function generated in the vicinity, knowing the incident wave potential. We also agree and understand that flow around the structure is generally assumed to remain attached, where separation is generally neglected. Fluid is assumed to be incompressible and irrotational, that is a standard assumption in any analysis in wave theories. structure is assumed to be rigid for the time being. Please understand, structure assumed to be rigid does not mean the member is fixed at the bottom. Rigidity can come not only from boundary condition, but also from the d by L ratio, that is diameter versus thickness ratio also. Okay. The structure or the member can still remain rigid. If this is d and this is t, then for d by t value of a specific number which has a categorical number in the design, you can always say the member is rigid. The rigidity does not only come from the boundary condition, of course it also comes from the boundary condition, and more importantly we also assume that the wave amplitude is relatively small. Interestingly, we will go ahead and try to understand that flow field in the neighborhood is generally described by the velocity potential. Velocity potential under the linear wave theory is given by the equation phi, which is written over there E minus omega t, which has got both the components, cosine and sine component, where phi is a spatial part of the total velocity potential and omega of course is the instant wave frequency which generates or hits the member. Now, the total potential of course in this case is going to be the sum of the potential of instant wave component and that of the scattered wave component, because the moment the wave or the wave particles comes and hit the member, all the wave particles do not pass the member at all, they also get scattered because of the interference effect, and that scattering or the volume of scattering and extent of scattering of course depends on, or the reflection depends on, what is the characteristic dimension of this member with respect to that of the wavelength, because the characteristic of the wave is quantified by two items. One is the amplitude, one is of course the amplitude, other is of course the wavelength. Wavelength in sense wave period actually, as you know wavelength and period are related. Amongst these two parameters already we just now said that wave amplitude is considered to be relatively small compared to the diameter or characteristic dimension of the member. We call this, we do not call this a diameter, we call this characteristic dimension. Why we call this characteristic dimension? Because this is actually the dimension which is forefronting the wave approach. Okay. For example, if you take an ellipse, major axis and minor axis, then which will be the characteristic dimension? Depends upon how do you orient the member. If you orient the member this way, then this becomes a characteristic dimension, or vice versa. So, depending upon the dimension of the characteristic value of the member with respect to that of the wavelength, then the water particle gets also scattered. Now, the forces will be generated by two modes. One is what we call as the sum of the potential of the instant wave component, and the other one is the potential of the scattered wave component. Having said this, let us closely look at the scattered wave component, because instant wave component we already have Airy's theory, for example, to explain me the water particle kinematics, which gives me in turn the forces on the member. The member may be fixed, then we have already given the equation yesterday, we know how to calculate the forces per unit length of the member. The member is floating, we already said yesterday how to calculate using the relative velocity component of the member and that of the water particle velocity. However, for the scattered wave component, generally the scattered wave component is normally represented by continuous distribution of waves. It is generally assumed as superposition of numerous waves. Now, then it becomes a boundary value problem. The boundary value problem defined in terms of Laplace partial differential equation is then now transformed to original partial differential equation in the potential flow theory, and the boundary condition now in this case will include ocean floor, free surface, submerged surface of the cylinder or the structure, and the radiation condition as the flow approaches infinity. So, there are different conditions you have got to specify in your numeric analysis when you start doing to capture the scattered wave component effect on the member. Having said this, let us look at what are those classical boundary conditions which we must use in case of numerical analysis. Let us say look at the bottom boundary condition. Generally in analysis the bottom is assumed to remain flat. However, in ocean bed flatness is not ensured and roughness is also not ensured. So, therefore, we however assume that the system or the sea bottom remains flat, because the distance of the flatness of the surface from that of the edge of the cylinder is very large compared to water depth of the seabed where the structure is installed. Therefore, the assumption is very much valid. We assume the flat bottom for the given sea surface at the bottom seabed. It also implies that the vertical component of the velocity now is practically 0 at the bottom the moment I say flat. If I say inclined or let us say rough terrain etc., it will have two components, one is horizontal, one will have the vertical component. To avoid this complexity, we assume the bottom is remaining flat, therefore, there is only one component which is along the inline force, the other one, the vertical component of this velocity, is remaining practically 0. Now, look at the free surface boundary condition, because we already have 3 surface. Please see here in this slide, we already said the boundary value problem or the boundary condition for a given problem should include the ocean floor, the free surface, and of course, the submerged surface of the member if the member is partially submerged. Okay. Now, so we just now saw the bottom boundary condition, we assume it to be flat. The free surface boundary condition equates the vertical component of the water particle velocity into the rate of change of free surface profile with respect to time. So, I am able to capture, or I am attempting to capture, the water particle velocity variation in the time domain, which will now help me to classify the free surface condition. It means the free surface boundary condition alone is capable of giving me the variable submergence effect on the given body, because the bottom will not give me, bottom is flat. Now, there is something called far field flow condition. What does it mean is that the body is located here, this is my incident wave field, this is my downstream far. Now, what is the influence of the far field on the body? Will it reflect back on the member? Will I have any interference on the successive member nearby depending upon the spacing of the member? I have to capture this also, because if I have successive members in one row, what we call group or cluster of cylinders or structure of members, then the interference effect on this member will be back on this member also. So, I must always classify what is my far field boundary condition or the flow condition, that states that the flow at infinity is only at an outgoing flow. Okay. That is a general assumption. Okay. Having said this, now we have to also discuss and define the body surface conditions of the system. Okay. The body surface boundary conditions again will have 2 forms. It actually depends on whether the structure is fixed or compliant. Please note, it is compliant. Okay. Compliant means floating, flexible. If the structure is fixed to the seabed, then the normal component already we said is going to remain 0. This is arrived from the basic assumption that no flow of fluid into or out of the surface structure is possible. Okay. Therefore, we say dou phi by dou eta or dou n, the normal, is actually set to 0. The quantity n is the direction normal at the surface and defines the outward normal to the surface, which is set to 0. Having said this, now for a compliant structure, of course, this will have different components in all the directions. Therefore, dou phi k by dou n, where it is going to be u and k, where k can vary from 1 to 6, where 1 to 6 are the number of degrees of freedom what this cylinder can accommodate for. One can ask me why I am limiting to 6, we already know this, but still let us, for the benefit of the users, let us try to specify this. I have a cylinder in plan, let us say I have 3 axes. Okay. So, I call this as x axis, this as y axis and this as z axis. I can have displacements along x, y and z, which we classically call as surge, sway and heave along zeta or z axis, and I also have rotations about these axes. So, to indicate the rotation direction, I normally put my thumb towards this direction. Remaining 4 fingers will have a specific direction plotted. I am marking that here. I call rotation about x axis as roll. I put my thumb here. I call this as pitch. I put my thumb here. I call this as my yaw. So, there are only 6 degrees of freedom a member can have in offshore structural analysis. So, we say that phi k will be the radiation potential of the kth value, where n k is a component of the normal in the kth direction, and u n k of course is the normal velocity component of the fluid particle at the surface of the structure, where k refers to the degrees of freedom varying from 1 to 6. Now, this problem becomes more complex, therefore, it cannot be solved using a conventional partial differential equation technique. So, we use Green's theorem or Green's function to solve this boundary value problem or boundary integral technique. This represents both the components of far field wave potential and the near field wave potential. Now, let us quickly see what is that so called boundary integral technique. According to this method, surface of the structure is divided into small elements. Okay? We divide the surface of the member into small segmental elements. These elements of course should represent true geometry of the structure in its planar surface. Okay? So, these elements are termed as lower order elements because of approximate representation. Hence, the method is also called otherwise as lower order boundary element method. The problem is then solved numerically. So, people use this. So, what they do is they do not try to find out the member force on the entire member, they try to divide the member surface into small finite elements and try to find out the numerical value of the water particle velocity and the force on these elements, and then integrate it for the entire length of the member to find the total force on the member, and then resolve this force in all equivalent respective degrees of freedom, okay, to get the force on the member. What we call as boundary integral technique or lower order element or lower order boundary element technique. Now, on the other hand, this will not suit because for large floating structures it becomes a problem. Please understand, when I say large floating structure, it is not largeness because of the diameter of the member, the structure itself is very large. Okay. So, the buoyancy force or the surface area occupied is very large. For example, FSRU, floating, storage, regasification units, they are very large in size, 190 meter long, 45 meter wide, and the design draft can be about 23 to 25 meters. They are very large floating systems. So, for large floating structures, the linear diffraction problem is solved for known scattered potential. We will have an example later. I will show you an example how the radiation potential, the velocity potential are being solved using analytical technique on applied to a TLP. I will show you later, but anyway we will try to understand that for large floating structures the linear diffraction problem is solved for a known scattered potential. Pressure in the fluid field is then given by the equation rho, which is I will show as minus rho dou phi by dou t, and knowing the pressure distribution center of each grid or the divided panel, then forces in 6 degrees of freedom then can resolve using this integration given as f of k, where I rho omega phi a phi s, where s actually is talking about the submerged area of the surface and I varies from 1 to 6 being the degrees of freedom of the given member. Now, in case of radiation problems, because when you have got a large floating system, the flow field will be interfered by the member and it result in what we call radiation potential additional to that of the scattered velocity potential. In case of radiation problems, radiation condition of the structure is imposed instead of diffraction condition. Now, structure oscillates in simple harmonic motion, it is an assumption to the absence of incident wave, then oscillation takes place in one particular degree of freedom at one time, that is an idealization. Corresponding radiation potential is computed using approximate surface boundary condition given on the system. Then the normal structure velocity is equated to the normal velocity attached to the fluid particle at the given point of the structure. This will now give rise to new 6 radiation potentials phi r k, where k is varying from 1 to 6 being the degrees of freedom. The total potential in waves now includes scattered and radiated. So, radiation potential is valid only for large floating structures, whereas scattered is valid when the characteristic dimension of the system, be it fixed or floating, has got some dimension relationship with that of the wavelength of the given body or the flow field. Okay. So, instant wave, scattered wave, radiated wave. Okay. We have got different potentials now being generated, and forces of course will come in all 6 degrees of freedom equivalent to all of them. Of course, phi r k is the forced oscillation of unit amplitude of the structure in still water in each degree of freedom, k being the number which is counted for each degree of freedom. Now, radiated potential provides added mass and damping coefficients. Why is it added mass? Because added mass again is a velocity, it is an acceleration term which comes from the additional acceleration component arising from the oscillation of the body given in the 6 degrees of freedom. Therefore, added mass. Why damping coefficient? Because this will induce and force damping on the given water body around the vicinity of the member, therefore damping coefficients. Now, they all will come into play in all 6 degrees of freedom, resolved accordingly. After obtaining hydrodynamic loading and coefficients, the linearized equation of motion is now solved. Okay, that is the procedure. As we said, damping estimates also becomes very important in case of offshore structures, because damping is a very important estimate in dynamic analysis as well. Damping is important in limiting excitation of the structure, we all know that. Offshore platforms are normally designed so that natural frequencies are well beyond the bandwidth or the dominant frequency of dynamic excitation. We know that because we already seen a curve where the design curve says my dominant frequency is in a specific range, whereas my natural frequency system is classically divided into 2 components, which is either very low or very high from the dominant wave frequency. In case of flexible structures, higher modes of vibration may result in more complexities which need to be handled very carefully, because they will give rise to secondary forces called springing and ringing action in the given flexible systems. So, we now understand in general that damping essentially arises from material. We know that because material degradation will also cause damping, and of course, it comes from hydrodynamic sources because we are talking about viscous damping. Material damping is present in the material of the members and the mechanical connections between the members or the joints or the connections. This is of course a Coulomb friction model, we already explained this in the earlier module. Material damping generally is small in comparison to the hydrodynamic damping. There are several sources of hydrodynamic damping which we also said in the first module lectures. Now there are two equations available on the screen now which will help you to estimate the damping very easily. For circular cylinder oscillating a small amplitude, Stokes has given an equivalent damping force which is given by the equation available as F is equal to pi v beta rho d square omega n square x, where x is the motion amplitude. So, it is proportional to the motion amplitude, where of course d is the characteristic dimension of the member. I keep on repeating this, it is not the diameter of the member, it is a member which is normal to the wavefront. Okay. Diameter of course in cylinder it is going to be the diameter, but does not always remain as the diameter, it is always called as characteristic dimension of the member. Okay. It is not the larger one. So, d of course rho is the density of the sea water and omega n is the natural frequency of the member which is vibrating. Whereas beta of course we have already seen yesterday that instead of explaining only the Reynolds number, people look at the ratio of the Reynolds Killigan Carpenter number, where therefore that is what the designers generally use in the analysis and design of offshore structures. Therefore, beta has been used here, where Stokes recommend a damping force per unit length of the member which is given by this equation. The damping force also given by a drag coefficient, where CD is not the drag coefficient here, it is actually the damping coefficient, is given by 3 pi square 2 k C pi beta. So, these are two alternative methods by which one can work out the damping force per unit length of the given member, which includes the hydrodynamic damping arising from the member. If we talk about damping in steady and oscillatory flow, the total damping structure arises from different sources. For example, it can be wave radiation damping, still water viscous damping, it can be wave drift damping, can be steady flow damping. I can give only one example of wave radiation damping. Let us say I have a cylinder whose characteristic dimension is known to me, whose thickness is or the d by t is significantly, the thickness is significantly low compared to that of the diameter. Of course, we must know that d by t is a very important number based on which the member is checked for its stability. You cannot keep the thickness so low compared to the diameter, the member will become highly flexible, so it will not remain stable. So, ABS, American Bureau of Shipping, gives us a guideline how to select a member whose d by t will be within a specific range. Okay. Otherwise, before the member fails in axial forces, the member will fail in buckling, okay, because it will not be stable. Okay. I have got a d by t which is proportionately available and accepted by ABS. Let us say I have an instant flow field, this is my inflow direction, and when the body interferes with the flow dimension of flow field, I have radiation potentials cost in all around, okay, around. Now, as you keep on seeing here, when they are getting radiated away from the source, they will start blocking the force or the action of the force on the member. Okay. So, there is always radiation damping cost, that is what we say here, wave radiation damping. This can be of two forms. One, because of the high amplitude motion of the cylinder itself, if the cylinder is flexible, or because of the rigidity of the member which reflects the forces or the wave particle hitting the member. Okay. So, it can be two forms, therefore, there is one important source of damping. Of course, in terms of waves, because they all arise from the structure, they also arise from the waves in terms of linear radiation damping, linear viscous damping and non-linear viscous damping. Of course, in so called models in the previous modules, we have only discussed about the viscous damping which is linear. We have not talked about non-linear viscous damping, because then it is called magnetorheological dampers. MR dampers, we will talk about this later in the third module. I will talk about. We have used MR dampers for one of the structural control in one of the tall buildings in Europe when we did some research there. I will talk about magnetorheological dampers. They are neither viscous nor friction based, neither Coulomb model nor viscous damping model. It is a combination of both actually, it has got both the components into it. So, MR dampers, so they can also create non-linear damping. We will talk about this later, where they are useful, how they are useful, we will talk about this when we talk about structural control in the last module, we will talk about this. So, damping can arise from two sources, one from the structure itself, one comes from the waves also. As you just now saw, radiation damping arises from linear diffraction theory. Loads caused by linear damping are proportional to the velocity of the structure, that is why it is called viscous related because they are proportional to velocity. Loads created by nonlinear damping are proportional to higher power of velocity, that is very important. If the velocity is very large for a high flexible member, then the damping arising from nonlinear component will be very high because they will be order of 3 or 2. Having said in both the lectures, we will talk about quick summary of what we have understood so far from fluid structure interaction as a summary. We already said presence of structure alters the fluid flow in its vicinity, it is very clear. Please understand, the influence of the member on the flow field is limited, it is not infinite, okay. That is why we always put the word vicinity. The flow field is only influenced by the member's interference only around its vicinity, not beyond that, okay. So, if you are able to construct one more member, that is why you know that is one of the important characteristic dimension, how you place the spacing of the column in a given TLP or place the columns in series of breakwater structures. What should be the spacing between the piles or the column members? So, you must always try to find out what would be that distance beyond which the interference of the member or fluid structure interaction becomes nullified, okay. Otherwise, it will cause secondary effects on the given member itself which will damage the member, okay. So, that is how the spacing is decided as far as the design is concerned. Now, when structures are placed in the flowing fluid, we have understood that the flow pattern is completely altered. We already said there is a shear happening, pressure differential happening. So, flow field is altered or flow pattern is altered. Restraints of course are developed in both fluid medium as well as in the structural medium also, both. And structure tries to gain its recentering capability, which results in additional force on the given medium, okay. That is very important. Inline forces, what we call drag, contain higher and smaller frequencies, both should be captured. The major difference between horizontal and vertical cylinder is the appearance of the lift force itself, okay. In case of horizontal, it is very simple, whereas vertical there is a differential shear happening. Horizontal cylinders will be also subjected to flow induced vibration, so they have to be very careful. In fact, the recent trend is people use this technique to harness wave energy, okay. They keep the member horizontal, they allow the member to vibrate, and the flow induced vibration caused by the cylinder on the body is captured, and they are trying to harness wave energy from this concept. So, this is a very, it will have a very interesting flow induced vibration characteristics. Ratio of turbulence to velocity variation across the horizontal cylinder is higher than that of the vertical cylinder, we have already seen in the last lecture. In horizontal cylinders, there is increase in shear parameter which results in increase in Strouhal's number, which in turn increases the vortex shedding frequency. Of course, at free surface, the vertical load in both positive and negative shear increases significantly in comparison to uniform flow. The dynamic vertical loads on the cylinder at the mid depth under positive and negative shear contain highest possible energy at very high frequencies. The steady component of vertical load increases significantly for horizontal cylinder only at the free surface. For dense structures which are closely spaced, the flow field slows down, we already saw that yesterday, as it travels through the structure. Load on the structure therefore increases, what we call this is a blockage effect. We already said what is the component of blockage effect. When wave passes the cylinder, it causes oscillation, inline force on the cylinder. If the dimension of the member is too large in comparison to the wavelength, flow remains attached to the cylinder. The radiated potential provides added mass and damping coefficients in all active 6 degrees of freedom. Damping can arise essentially from material and hydrodynamic sources. Material damping is present in the material itself because of the mechanical connections. This is a Coulomb friction model. Material damping is generally small in comparison to hydrodynamic damping. Loads caused by linear damping are proportional to velocity of the structure. However, when the loads are caused because of non-linear damping, they will be proportional to either square or cube of the velocity of the structure. Lift forces contain oscillatory components with multiple frequencies. For uniform flow, force on cylinder can be decided on the basis of either Reynolds number or Strouhal's number. However, people look at the ratio of these two numbers for the design. Vortex shedding dominates the types of vibration caused by the cylinder placed in the fluid flow. Boundary effects and end effects on cylinder introduces 3D effect in the flow past the cylinder for finite length. So, having understood this brief summary on FSI, we will start with applying dynamic analysis and design for different kinds of structures. In this example class, I will take about a fixed type structure. I will touch upon some of the aspects of software application on this, how it has been used. I will touch upon SACS, how it is done. So, we will have about 10-15 slides to teach you how fixed type structure generally analyzed statically and then dynamic analysis done. Of course, I will solve it later by using a classical equation of motion subsequently. We all know that fixed type structures are classified as drilling and production platforms based on the functional use. Jacket structures are fixed to the seabed, we already saw that in the earlier module. Generally piles are used to anchor them to the seabed. The size, the number of legs, the deck size depends on the requirements of the deck and the functional use, because they are form dominated or not function dominated. Generally the classical system what you see here is a truss based system, which is a transparent system, that is why we call the template structures. So, that is the steel jacket at the bottom, and top side is called the top side module, which is modular construction. There are different types of analysis you do for a jacket. One is called in service analysis and other is pre service analysis. In service analysis comprises of in place analysis, modal analysis, fatigue analysis, seismic and vibration analysis, whereas pre service analysis also looks at load out analysis, tow analysis and launch analysis and flotation analysis, appending analysis, offshore lift analysis, structural designs of paddies and trunnions, and of course analysis and design of sea fasteners. So, you can clearly see there are two categories of analysis, a set of analysis being done for jacket structures. One is to classify the member dimension, one is to facilitate the construction or erection of the member. Okay, both are important. Friends, it is very important for us to realize that the second kind of analysis what we do is only and uniquely applied to offshore structures alone. Okay, land based structure, onshore structure do not have any complexity on pre-service analysis, okay, because the complexity generally arise in installation and commissioning or decommissioning of offshore platform compared to that of the design itself. Okay, the members will fail, may fail when they are being launched or towed or analyzed or let us say floated or appended. Okay, these are operational stages. In case of an installation of jacket structure, the slide below shows you, the figure here shows you one of the appending stage of the template leg. So, talk about one typical analysis, which is in place analysis. The schematic figure of the jacket as generated on the software is shown here. The top side is again a truss system, the seabed is marked or the sea level, free surface level is marked. Jacket again is a compression or a combination of different members, vertical, horizontal and inclined members, which are braces. Seabed of course is a fixed flat bottom, and of course piles will anchor the fixed the legs, the template structures to the bottom using a anchored connection. The purpose of in place analysis actually is to know the structural deflection and stress levels in the service condition. So, it does not do any dynamic analysis in general, it wants to know what would be the structural deflection criteria, is it going to be very large or very small or insignificant, and what would be the stresses generated because of the displacements caused on the member by the forces acting on the member. Why we want to find out this? Because of two reasons. One, to find out the possible loading conditions or favorable loading conditions, or what are the possible directions where you can orient the members when you are analyzing or when you are installing. So, you do a preliminary design based on this, because your member or the structure should not fail when you install them or decommission them. You do a preliminary design, you identify the applicable design codes, specifications and design criteria, gather the relevant geological environmental data, then establish appropriate loading conditions, choose an appropriate configuration of the member, select the most suitable member sizes, okay. Evaluate the dynamic performance, the reserve strength. Generally the most important consideration in static analysis in jacket structures is what we call unitary check. We will talk about that slightly in the next slide, I will show you that. So, there are different design codes available, which you can also read from other parallel courses where people teach design of offshore structures. APRP2A, AISC, DNV rules, AWS rules for welding codes, and DOE offshore installation guidance and design and construction certification. Let us quickly see what are those environmental data related to water depth which we must collect if you want to do an analysis for offshore structural systems. Wind waves, current, wind generated waves and tidal and tide. Tide will have both astronomical and storm surge part. Of course, the drag and inertia coefficients given in the specific area, marine growth intensity, soil and foundation categories in terms of ultimate capacity and load deflection criteria for a given pile design. Of course, earthquakes available in the specific sector, which will result maybe a response spectra or at least ground motion or peak ground acceleration time history should be available to me as an input data, which are geological and environmental data available to me for a given water depth where the system will be installed. What are different kinds of loading? We already saw that in the last lecture f of t in the last module, but still let us focus it back again. Dead loads can be structural, architectural, equipment, piping and erection and commissioning. Live loads, storage, personnel or people, crane lifting weights in helicopters. Environmental loads, wind, wave, current, tidal variations, wave directions and earthquakes. Accidental loads, board impact, explosion, blast loads, fire and explosion and dropped objects, that is very important. Pre-service loads like motion force and mating forces. Now, to ensure that the truss system remains stable, we go for different kinds of bracing system. These are typical bracing system adopted in case of jacket structures. The diagonal bracing system, this is also a diagonal bracing system. The only difference in these two cases is that this is mirror reflection of the other. Okay. This is unidirectional, this one is all unidirectional oriented, whereas this is mirror. The other one is an X bracing, which you can see the shape is X, and the other one is a K bracing. It looks like V, actually it is a K. If you look at this is the K. There is a member and there is a member. This is a K. That is why it is K connection. Typical horizontal framing based system is also available on the deck, diagonal, rhombus, V, X, etc. Now, there are some guidelines available for finding out the minimum member sizing. Please understand, offshore structural design is more or less predefined by the codes. We do not have a choice of selecting a member or diameter or thickness as my choice. More or less they are predefined depending upon the KL by R ratio, which is the deflection parameter or the stability parameter, other is as I said the d by t value. Okay, it is very important. So, both on based on these two parameters, depending upon the range available for K being effective length factor, L being unbraced length, and of course, radius gyration is remaining R. We all know this how to compute them because they are basically part of fundamental mechanics for a given member, which is tubular member. For any dominant direction, let us say xx or yy, I must compute the moment of inertia, I must know the cross section area, I will get the radius of gyration in that direction, not necessarily least, I am talking about I value or R value. And of course, if this member is having connections in the top and bottom which are both in fixed, let us say, and I have a member, I should be able to compute what is the unsupported length. Please do not multiply any factor here. Okay. Do not try to work out L effective, try only the unsupported length, that is the connection from that top to the bottom. So, L is an unbraced or unsupported length. Of course, the K factor is an effective length factor depending upon the boundary condition which can be imposed on your multiplier. So, you have a range depending upon that, also depends on what application you look at, primary braces, secondary braces, joint cans and legs and piles, what should be the kind of member sizing or preliminary member sizing available for a given system. It is available in generally in design codes. There are different load combinations people used to design the system for. Storm conditions maximum topside load, that is one worst combination. The other combination can be operating condition maximum topside load. Third could be storm condition with minimum topside load, and fourth can be load combination factors and weight contingency effects on the given system. These are different combinations apart from dead, live load, wind load combination etc., which are categorically discussed and abbreviated in the previous module lectures. Generally, code recommends an unitary check, which I said few minutes back. Members should be checked for the stresses depending upon the yield strength, effective length and K factors, CM value and compression flange unbraced length. They are also checked for joint punching shear because you have got K connections, X connections etc. in the bracings. One check for the joint punching shear, where you look at the yield strength and 2/3 of the tensile strength of the member, and joint classification and the load path. You can also look at the pile penetration, where we check the ultimate axial capacity of the pile, the scour depth and the factor of safety for which the pile can resist the lateral loads coming on the system. Let us quickly see what are those steps in a jacket modeling in SACS in general for in place analysis. Define the basic jacket framing, use the jacket wizard in Precede Pro in SACS module, which defines the leg batter, the conductor spacing and leg and the skirt pile details. Title this file as an input as SAC INP star dot star. The file contains the model data, the member properties, the CDCM value, the wind areas and the load data and the marine growth etc. You can also group them, you can also section them. Create a joint can check input file called joint JCN-INP. So, standard modules available in SACS where the load cases for which joint unity check needs to be performed. Select linear static with PSA analysis option in the run file wizard. Now, please understand here we are talking about a static analysis which is also linear. Okay. The output file specifies the pile capacity mobilized versus the capacity required, giving a unitary check for your value. Open the PSB folder and check the member UC ratios graphically. One typical plot is available now in the second slide. So, this is a typical screen capture available for creating a new model. You can add the members as you see from here. Then a typical result is available as an example here. Jacket has been created with the RL of -40 to +10 about 50 meter. Row A and row B are the two rows of piles available or the jacket legs available at different levels as -10, -20, -30. The bracing points are connected in the analysis. The deck is about 10 meter by 10 meter square. The load data is being used as wave data, significant wave height 8 meters and wave period 12 seconds and wave direction is 0. Then unitary check with and without Marine growth has been done, and you will see, for example, look at this specific member. Let us say look at this member. This member is having the number of 0.04, it is a unitary check, so it is safe. It means if the number does not exceed 1, it is safe. So, you can check for every member. This member is having 0.32, which may be one of the critical member. All other members are practically close to 0, it means they are very rigid and very safe. Okay. This member is having 0.36, it is not 0.36, 0.08, 0.20, 0.51, okay, 0.02, etc. They are very nominal. Okay, this is 0.06, do not read as 90.0, this is written in this other way is 0.06 and so on. Okay. That is how it can be easily done and generated from the software itself directly. So, essential check for stability or in place in service analysis is that unitary check, which essentially check the clears of the members from the stress levels. Once it is done for static analysis, we go for dynamic analysis. So, the standard equation of motion, which is very familiar to all of us, we know that. Now, the only term which we do not know, which is very specific in offshore structures, is MA, the added mass term. Okay, how do we get this term? So, we will take up an example and arrive or derive this added mass for different systems. I will show you how it is done. Otherwise, all other terminology are very familiar to us, F of t, K, C, MA or M, etc. We know the classical equation of motion. We also do pile soil interaction for jackets because they are embedded on seabed. Jacket can be modeled up to the foundation level. The pile soil interaction is generally modeled using a lateral and vertical springs. Okay, that is the general procedure what people do along the length of the pile at each segment of the pile. This has been supported by Mohammed et al. In 2011, which the reference is available there directly from the EIJC journal directly at indicated there in 2011. So, piles are generally modeled as lateral and vertical springs and the actions are transferred to the pile system for analysis and design. So, this is what we are going to summarize now in fluid structure interaction in this class, and we will talk about the different applications. I will classically introduce one important application now, which we will discuss in the next lecture of course. So, when you talk about let us say the offshore structures, okay. Now, people initially started designing them for no response, maybe jacket structures, fixed base, water base, GBS, etc. Subsequently, people said this is of no use because they are highly uneconomical and decommissioning them, installation taking a lot of time, the return time available in terms of economy is very low. So, you do not want that. Then people said you design them to remain as floating or what we call as compliant. So, today I have a system at location A, I have no oil at A, remove it from A and make it to B. I want to make it completely versatile. In fact, people are very keen interested to know, can I have a ship or a floating system where I keep on exploring oil continuously along x and y kilometer area for a given day. So, that is the hypothetical thing. Okay. So, compliant systems. In both these cases, maybe till 2000, okay, I can say that year 2000, people have been only commissioning new systems and installing new. So, the focus was essentially on forms, structural forms and new designs, structural designs, and of course, new material, there is no doubt about it, new materials for top side, bottom, etc. Now the present trend from 2010 onwards, the present trend is people are not interested in actually investing more on new structural forms, being floating, being fixed. They are not interested. What they want to know is extension of service life, of the existing platforms, because right from 70s till 2000, about 30-35 years bracket, people have constructed more than 1500 platforms elsewhere, okay, in Gulf of Mexico. Now people cannot and need not and should not abandon all of them, because some of them may be useful, okay. So you cannot abandon all of them, because decommissioning and abandoning them also costs. Therefore people are interested to know, can I extend the service life? So now the important focus which has been drifted in offshore structural engineering now, and we all agree, and you also study economics, you know that now the oil price being very high now, there is lot of retrenchment happening in oil industry in terms of recruitment. There is no new projects or new investments being happening in oil industry for the past maybe 1 year close. How long it will continue, nobody knows. Now the basic reason is you cannot keep on investing on new forms and designs and keep on exploring at greater water depths, because greater water depth, greater exploration, it will cost you more and more. There is no guarantee of the return back again. Therefore people are interested, can I extend the existing form to some more years, so that I need not have to invest much more, but I can still draw some money. Therefore retrofitting, rehabilitation has become a very hyper word now in offshore engineering. The people wanted to know really that, can I strengthen my existing members? Generally if you look at these two words as a coin, people generally say I have a system, maybe a cylindrical member, a system, a block subjected to force, the block responds, the block becomes weak, force does not become weak, force is getting intensified, okay, force keeps on changing, there is no weakness. Block becomes weak because of material degradation, what we call aging effect, okay, aging effect, it becomes weak. So generally retrofitting is always focused to strengthening the member. How do they do is, there are many techniques available. To be very rough and crude to say, they try to put a cover over this and strengthen the member. Now to do strengthening of the member, you have got to shut down the member or shut down the platform for some time. The moment you shut down the platform, the whole exercise of economy will be questioned. So you cannot do that, okay. And strengthening of the member is a very important idea which has been applied to many members offshore and onshore. But now the latest trend is, do not strengthen the member, let the member be as it is, reduce the forces on the member. Now the best part is this environmental factor, you cannot reduce the force actually by any technique. So what they do is, they have a member, you put a cover over the member and protect the member and sacrifice the cover and keep on changing the cover, because cover is not to be put for the entire length or the entire depth of the member, because the member is not uniformly damaged for the entire height of the member, it is only partial damages are happening. Even if you look at the strengthening part, people do not strengthen the entire member, they only strengthen possibly the joints or the connections, only few points they will strengthen. So those points which are weak in strength point of view, only protect them. So one can ask me a question, by protecting this, by putting a cover over this, how the force are reduced? Because I am not doing anything with the force, okay. I mean if I put any external agency, reduce the current velocity, reduce the water particle velocity, it is fine, but I am only putting a cover, okay. This is a very interesting appreciation idea which is generally used for floating temporary structures, because floating temporary structures which are generally used for naval application, for example let us say I have a capsized submarine, I want to repair the submarine, it is capsized completely, I have a platform, I have a jetty, I have a vessel, I have a cargo which is very important strategically, it has been capsized, I want to repair it instantaneously, I want to service it. So I have to create a temporary platform. There I cannot imagine of going for any kind of this system where I invest on very huge type of form based designs and construct a platform, then repair the vessel, vessel will go off, platform will remain there, what to do with the platform? So we cannot do that, afford to do that. So what people do is, they go for floating temporary connections. Any floating temporary connection which are compliant in nature, should attract less forces, otherwise the floating system will get on floating, you cannot do any repair operation at all. So, there should be a technique available to reduce the force. So, people have attempted this, first time this was attempted and understood at Tensilic platform which is Mars. There is a hurricane which spoiled this Mars platform completely, it was put down for operation for 2 years, there was no production in this platform. Okay. So, people attempted this, they hypothetically thought can I reduce the force, they put a cover, then they left it conceptualized, that is all. So, research has taken place in different fronts. This component of reducing force is a new idea for offshore structures, but it has been a very common idea in all coastal structures. Wherever coastal structures are there, people use this for many years. Ekofisk is one example. Ekofisk platform is one classical example where people use perforated members to reduce the force on the coastal jetty. People have used this, but in offshore structures, for strength protection point of view, people have never attempted this at all, but only they gave an idea Mars TLP can do this in experimental study. So, in the next lecture, we have got a very interesting study done for the one of the important government agency in India, where we attempted to classify some important study. We will discuss partly about that, the technique available, and one interesting results where we will show you how numerically step by step the study can be done, how experimentally step by step the study can be done, what do you get from the outcome of the study, which of course in hydrodynamic analysis, it is not purely dynamic analysis, because I am talking about fluid structure interaction part, dynamic and hydrodynamic analysis, which will be discussed in the next lecture tomorrow. We will talk about that in 45 minutes. So, some results will be given to you, and more interestingly the design aids are developed which can be directly used if you want really design an outer cover for a damaged member directly. In one click you can design the system, select the outer cover, place it over the existing member, the member will get rid of the forces coming on the system. It is readily available. Of course, the outcome of the design is depending upon the rigorous numerical analysis, which is validated experimentally, analytically and numerically, accepted, published and patented more than about 10 international journals. So, we will talk about that tomorrow in one of the important study. That will be very interesting part to make you to understand and believe that hydrodynamic analysis can be, or the dynamic analysis tool can be useful in a practical application like this, which is an hot spot area of application now in ocean engineering or offshore structural engineering. Do you have any questions here now? So, we stop here, and I have given you some preamble about the jacket analysis. I will take up different forms of offshore structures like TLPs etc. in the subsequent lectures in this module. We will talk about detailed dynamic analysis step by step in all these cases. We will give you the equation of motion, derive the stiffness matrices here. We will of course solve them in the numerical method. I will give you the results only, because the algorithm will be given to you, but numerical analysis cannot be done here. I will give you the results directly referring to the published papers, where you can read the papers and understand how they have been represented. That is the idea in this module. So, we will start with the retrofitting part tomorrow, then we will go ahead with this. Okay? Thank you.